This is a population model we already know. We've seen it before. So X, Y, these two are functions of T, but I do not always write X parentheses T, but when you see the derivatives, you know this prime in this equation. This prime means rate of change with respect to time. So although on both sides of the equation system, we don't see the parentheses T, it's only for the simple format, but you should keep in mind. So there is an independent variable T. So this system is called autonomous system because the right-hand side of each equation does not depend the variable T explicitly. So this is an autonomous system. By the way, if we write this equation simply by changing the names of the two equations, it's still the same system. So let's try to show the same system in a different way. So we can see the X, let's call it X1, the first unknown function. Y as X2, so we can write into a vector valued function whose derivative is equal to negative X1. So X1, X2, because to replace X and Y. So Y is now denoted by X2. So as you can see here, this is simply rewrite the system. Yeah, they're the same, except I changed the name of the two dependent variables. Right, so now, what's the advantage of this notation? Since if you have more equations in the system, you can have up to n components. Then in that case, this notation is convenient. So we already know this problem can be represented by a single letter if this X, this is our X vector, so we can write it as X derivative equals the right-hand side is some vector which is depend on the component of X. So as you can see, there's different ways of representing the same problem. So here's from the XY representation, right? We can simply change the name into two equations of X1, X2. And we can even write it into the single equation form. So the X is the vector valued function X. So just to recognize the notation, and this capital X here will be this vector, which we call vector field. So let's quickly look at this notation. So if we have n components for this vector, then we have x, the vector which has n components, right? So this x vector has n components, x1, x2, all the way to xn. So we put the 3 dots, and the right-hand side is another vector, because the derivative of x vector is equal to another vector. So this capital X is another vector which has also n components. And the first component of the right-hand side vector is denoted by capital X1. Second component is capital X2. So we have n components of this right-hand side vector. And this each component of capital X depends on the lowercase x. Yes, that means it depends on each component of the lowercase x. So you see the two forms, they are equivalent because one is just simply written as name of the vector, right? This is the one form. The other is the component form of the same system. So they are the same. The only difference is the format. So we talked about the solutions. In order for the solution curve, which is denoted by alpha, so the solution curve alpha, which is a vector valued function of t, for this to be a solution to the given system, alpha has to be differentiable, right? Because in the equation, alpha has to be differentiable. Alpha also has to be in the domain of the capital X. Otherwise, this alpha does not make the problem a meaningful problem. On top of that, alpha has to make the left-hand side equal to the right-hand side. That means if you substitute alpha curve into either side of the equation, so alpha derivative should be equal to capital X at alpha. So those are the conditions for the alpha to be a solution of the system. Once we, so that is a quick review on what do we mean by solution? Yeah, solution is just a solution, a vector valued function of t, which we call alpha. Alpha at t, so the t is from a certain interval. Alpha of t is a real valued vector. So then the alpha has to be differentiable because of the equation system. And alpha has to be in the domain of the vector field. And also alpha has to make this equation true. So that will define a solution. So with all those conditions are met, then alpha, if for n and t, alpha of t derivative is equal to capital X at alpha of t, then this alpha is the solution curve. Before we solve such a system, we can just simply quickly understand the capital X. Why the capital X is called a vector field. So that is, whenever you give an X is like input, right? Input vector for the capital X. So this capital X is a mapping, maps each little x, lowercase x vector into a new vector. Suppose if you at this location x, and I have a direction associated with this x. So after this mapping, you get a new vector, which is indicated. So if you pick another x, you may have another direction. And a different x will give you a different capital X. So these are just the different possible locations of x. So certainly you can have, for example, 3 more locations of lowercase x at each such x. We can based on the capital X, this is the mapping after capital X, we will get a new vector, right, indicating the length and direction of capital X. So, for example, could be something like this. So those vectors I put are the capital X at each possible point, lowercase x. So the vector field, let's try to imagine a curve. So the curve will be the axis that whose rate, that means the derivative of x, will agree with the vector field. So if we have this vector field, then we try to describe the x, then so this x will go along with this curve, right? So something like at this location x, then its tangent vector will be same as the capital X. So you can do some description of solution curve based on the vector field. So this vector field at each x, that is the image, capital X, at each lowercase x is an image of lowercase x. But this image is a vector. And if you want to find a unit vector, you just divide the length of this vector, then you get a unit vector. So that way, the vector field, for example, if you draw at different locations of x, right? Suppose we have 6 different locations of those x, and the capital X at each one of the location will be a vector. Yeah, so you can try to show that. But once we divide, so this is the vector, then you can try to describe a curve that go along with the vector field. So then the curve can be predicted based on the vector field, because your curve should be a curve that is tangent to this, to each arrow. So if we want to describe a certain curve, for example, the curve passing this point will be tangent to that one, so etc. So a curve passing through this point will be tangent to this one and then this one, etc. So you can try to imagine some curves and how, based on the field, how they flow in based on the field. So that is the field, but those little arrows means at each location of the domain of the map, capital X, then you can indicate a direction. So this capital X, once we normalize it, we get a unit vector. But yeah, so this is a unit vector. You can indicate little arrows of the same length. And you can even scale it by multiplying this unit vector by a k. So that will be k times this. So that means each vector of this in this vector field, portrait in the vector field will have the length k. So that is one way to make the vector field very nicely indicated with little arrows. So now I want to give a system that is non-autonomous. So so let's get the from the population model, we have generalized the model into a problem of this. So the right-hand side means the vector field depends on X, right? Or each component of X, but does not depend on T, the T variable independently. So actually this, we don't see the T. So if we have a system with a vector field depending on T explicitly, then this system is called non-autonomous. And the first case, when the vector field does not depend on T, although implicitly depends on T because this little x, right, is depending on T. So therefore, the vector field depends on T, but not explicitly. So if the vector field does not depend on T explicitly, it is called autonomous system. So it's very easy to tell which one is an autonomous system, which one is a non-autonomous system. So let's look at a system that is autonomous. So here's one example. Suppose I have x1, x2, and derivative of this vector is x2 negative 10 sine x1 minus x2. So you can see this example is given it is an autonomous system. The reason is because as you can see, the vector, which is x1, x2, right? This is x. And the right-hand side depends on only x. You can see it depends on only the components of the x vector, right? So the first component of the vector field depends on only the components of the x vector. So we have an autonomous system. We don't see the t variable. And let's look at an example of a non-autonomous system. This example, suppose I have, again, two equations in the system. So the first derivative of x1 is x1 plus x2 squared plus t. And the second one, x2 minus x1. So this example is non-autonomous because, as you can see, the vector field, this right-hand side, depends on t. Yes, t appears. It explicitly as a variable in the vector field. Okay, so it's easy to see that autonomous and non-autonomous, the difference, right, all based on the t variable. So here t appears explicitly and it's non-autonomous. The first example is autonomous because there's no dependence on t. And we want to see for autonomous system. So if you have an autonomous system, and very conveniently, we can find fixed points. Fixed points are also just the constant solutions of the system. So meaning the capital X, the vector field at each of the fixed points, you get 0, right? Because if the solution is a constant vector, then the derivative of the solution will be 0. So that if you are looking for constant solution vectors for the system, then this derivative will become 0. So you just solve equation system that does not involve derivatives. So fixed points are easy to solve. Just all the solutions that satisfy this equation. Yeah, so you set vector field to 0, then you solve for x. If you can find all the constant vectors x, then you have found all the fixed points of the given system. Another type of problem is initial value problems. So initial value problems. Okay. Initial value. So an initial value problem is a problem of this form. Suppose I have a first order, let's say, non-autonomous system of equations. In addition to the equations, we also know the vector passes through a point. So that is at a certain t, the value of the solution is given. So this is an initial value problem. Abbreviation for the initial value problem, IVP, is the abbreviation for this kind of problems. So let's just try a single equation. So suppose I have one single equation involving an unknown function y. Y derivative is equal to the right-hand side, let's say 3. So the right-hand side is just a constant value 3. So here, as simple as this is a function y whose derivative is just 3. So with that being given, so that is the equation. And also I want to specify y at a certain t, okay, t naught, right? So I can say at 1, it is 5. So this, what does that mean? This is a very familiar problem you've solved before. So let's quickly solve it. Y derivative is 3, so y, but taking, it's a group of lines, right, with slope of 3. So y must be 3t plus a constant. So from the first equation, we know all such straight lines will satisfy the differential equation. However, we want to decide a line that will satisfy the initial data as well. That means when t is 1, my y value has to be 5. So let's quickly decide. So not all these straight lines will pass through this point, 1, 5. Let's say which one will pass through. So if t is 1, y has to be 5. So then from this, we can see the c has to be 5 minus 3, which is 2. So we found a group of functions will satisfy the first differential equation. However, only when c is 2, that particular curve 3t plus 2 will satisfy not only the first equation, but also will pass through the point 1, 5. 1, 5. So then we found one unique curve that is from all the solutions, right, with the slope 3, all the lines, there's one line that will satisfy this initial data. So when t is 1, y is 5. So then we pick out that one line as a solution to the initial value problem. So initial value problem is good because we have sometimes we can have a unique solution to that problem. Now, even if you have a initial value problem, that does not guarantee us to always have a unique solution. So, but with appropriate properties for this problem, it's possible we can have a well-posed problem and uniqueness of a solution, etc. So now, suppose I have higher order equations. Can I always reduce higher order equations to first order equation? So let's think of reduction. And we want to reduce a higher order to first order system. Also, in case the system is non-autonomous, we hope to reduce it to first order and autonomous. So that is our goal for a higher order system of equations. We want to reduce it to first order. If it's not autonomous, we also want to get an autonomous first order system. So we will look at an example in the next short video.